Hi, my name is Christopher Hyatt, and this is the magnetic field of a bar magnet experiment. As a brief introduction, the purpose of this lab is to explore measuring the uh, quantitative bits of a bar magnet and quantifying its magnetic field. Some fundamental physical principles you need to know in order to understand this are the magnetic force, shown in the bottom right, and exponential growth, as shown in the bottom left, because we will be linearizing an exponential equation. The main result of this lab will show that using these two fundamental physical principles, you can understand quantitatively how a bar magnet works and calculate the physical constants around it. As a brief explanation of the experiment, we use the magnometer in our phones and a bar magnet in order to calculate the magnetic field at different locations from the bar magnet. The initial conditions are the same as the final conditions. They're exactly as shown in the image because the experiment was static. The system is the phone, the magnet, the Earth, and the rest of the universe. And there are no surroundings. There's no energy change or anything. So our calculated N value from the experiment was negative 2.4834, which we'll see further in the next slide, and our observed and calculated 45-degree measurement, as seen in the image before, was 0.0000289 teslas, and the computed 45-degree measurement, which we'll see later in the coding portion, was 0.0000425 teslas. Here is the spreadsheet with all of the data used for this experiment. We can see here our linearized version of our logarithmic equation, that we use to calculate the N value and the K value. Next up is the code. Here we can see my computed model in the first part of my code. The first part of my code is just initializing a few variables, and then similarities and differences between the data and the model include that the model has very few errors compared to the data gathered before due to its lack of errors. Sources of error include user mismanagement, and also potentially me getting the magnet too close to my magnometer and it zeroing out a couple times, then my compass started pointing in a different direction, so that might have messed it up. Here are the next two parts of my code where you can see me creating the vectors that were surrounding the magnet in the image before, as well as an additional little thing I added at the end where it's showing bmag for my own uses for a couple slides ago. Next up is the discussion. What if, in the experiment, you oriented your setup so as to compensate for magnetic north? What if you hadn't done that, and had instead laid out your meter stick at some intermediate angle with respect to Earth's magnetic field? How would your results have changed? And I said if this had occurred, you would not have been able to differentiate the magnetic field of the bar magnet from the magnetic field of the Earth without more complicated math involving geometry. Therefore, the way we did our setup made the math significantly easier. The next what if is, imagine you had two identical magnets. What if you redid the experiment, but instead of using a single magnet, you used the two identical magnets stuck together end to end? How would you expect your measurements to differ? The measurements would increase because the formula for magnetic dipole moment increases as volume increases. If you remember, the formula for magnetic dipole moment involves the area, and so I made the assumption that that extends to volume, and so I said it should theoretically double with a doubled amount of volume. In conclusion, we are able to use those fundamental principles mentioned earlier in order to calculate the magnetic field of a bar magnet without too much trouble. In general, magnetic fields are quantifiable and real things that we can work with. Thank you.